networks and especially mesh networks on layer 2 with more than 1,000 devices. In my experience, it's already difficult with 500 devices because find a switch with 500 ports is difficult. You wanna do it with 1,000? I'm interested. I hope everyone else is also. So, brighten us.
Thank you, for your introduction. Like you said, I'm Linus, and I thought now that we have some Fryphone communities who are actually flying Batman Advanced at an altitude of 1,000 nodes, it might be a time to give a little presentation about how we do this, what measures we took to actually compensate some of the issues which are inherent with layer 2 networks. So, little disclaimer first. I think when you're starting to use the words second layer and scaling in one sentence, it can sometimes result in heated debates. So the emergency exit, I think, is over there. Or I also like this sketch very much. I don't know if anybody of you knows Abbott and Costello. It's a little old, but I think it was also already nominated for the best sketch of the 20th century. And they are arguing a lot they want to argue about baseball, but actually they don't really come to this because they are just arguing about who's on first, what's on second. I don't know what's on third base, and yeah. So what's on second for us? Not baseball, but in this case, Batman Advanced. So Batman Advanced, that's what I'm going to start with, about the measures we're taking there. And then I'm going to continue with Gluon, the mesh framework we are using for many Fryphone communities. And I'm trying to show a few graphs so that you can have some impression how it looks like, what the current issues might be, which issues we might have solved, and which issues might be remaining. So I'm starting with Batman. Batman Advanced, it's a layer 2 mesh routing protocol, which means compared to a layer 3 routing protocol, it's forwarding frames instead of packets. How does it do this? It does this by encapsulation. So what is encapsulation? How can you imagine this? Well, it's like instead of letting your IP packets wander off on their own, here with little cat pictures in their mind, instead we are encapsulating it into a frame. And with this frame, we have a few gains we get from this. One of the gains is that it's network protocol agnostic. So we do not care if your IP packets are talking IP version 6 or IP version 4 or maybe something totally obscure or your own protocol. We just forward that. The second thing is we have fast client roaming. So if your host device is changing the access point it's using, it's switching from one AP to another, Batman Advanced takes care that there's no interruption for the client service. And then we can also do, because we're doing tunneling, we can do funny things like network coding, bonding, and so on. And even without the passengers noticing that we might have been driving upside down the whole way. In the end, we just decapsulate everything, and it looks as if nothing fancy has happened. So to be frank, though, this usually looks more fun to drive upside down. For network coding, it's not, in practice, at least the implementation in Batman Advanced, it's not really having much of an advantage yet. So, and the fourth advantage is that we have broadcasting. So you can send one message, and this message is delivered to every host in the network. And as you might think, this also is the biggest disadvantage we have from layer 2 mesh networking. So that's what I'm going to mainly talk about the broadcasts we have in a layer 2 mesh network. So the bad news is we do actually have quite a significant amount of broadcast packets. So we see here the red line, that's the multicast traffic we are having on top of, or which is layer 2 specific. So in this case it's 66 kilobyte per second. And I've picked the Fryphone Darmstadt network because it currently has about 650 nodes and it's running a relatively recent version of Batman Advanced as well as Gluon. So yeah, and they on average have about 1,500 clients. So, and you can already see that the number of clients is changing over time. It's reflected in this graph. This capture is done for 5 hours from 6 a.m. to 11 a.m. And you can see that, well, a lot of, or some more people are waking up at 7:30 and the graph starts to grow. And on the other hand, I've also have inserted this green line here. It's the OGMs, the originator messages, which are the packets that batman-adv is using to actually build up the topology, to distribute the routing knowledge. So, and you can also see that this one, the green line here, 61 kilobits per second, is actually rather constant. So we can already see in this graph that the number of nodes in our networks is not changing that much. For a day, it's usually staying about the same number, while the clients, it's changing over time. So the rest, so this capture was done, I think I did it with configuring a mesh node to have meshing on a LAN port, and on this LAN port I've measured the packets that are coming in. Despite from these OGMs and multicast packets, there's not much other thing going on. So this is basically the sum of all the overhead we're currently having. Yeah, so how do we tackle this? One of the overheads we're having with layer 2 and multicast is that hosts need to obtain some IP address, and one of these things is usually done via DHCP and IPv4, and for that we have DHCP requests and discover messages which are broadcasted. So classically, batman-adv was just flooding these messages through the whole network. However, one of the very early optimizations was to have the ability to mark some of these nodes as gateway servers. So those are marked here, 3 ones, and batman-adv will then decide, on, depending on its own metric, to choose the best gateway available, so which is kind of the closest one from the Batman perspective. So instead of broadcasting it through the whole network, we're sending it to the gateway next to it, the closest one. So, okay, so now we have an IP address with IPv4. Then we have a second protocol, which is causing quite a lot of overhead in a layer 2 network. When this client wants to communicate to some other client, it needs to resolve the IP address to a MAC address. And for this, we have ARP. And very early, Antonio implemented a distributed ARP table in batman-adv. So the idea is to spread the whole knowledge of the ARP table through the network. And whenever a client wants to resolve an IP address, it instead can send specific unicast packets to a bunch of hosts instead of bothering the whole network. So that's been implemented in batman-adv. And that's basically already the essentials for IPv4. So great, these are already tackled. What about IPv6, the new stuff? Or what about things like service discovery protocols, LLMNR, MDNS, and so on? They're also quite noisy, like your printer wants to announce that it's there, and you might have some Samba file sharing or whatever. So what about that? Well, a little break before I continue with IPv6. I want to talk a little about what we are doing with Gluon. So Gluon, the architecture looks about like this. So a node typically has 2 Wi-Fi interfaces. One Wi-Fi interface, it's facing the client devices we have here, like your laptop, mobile phone. They're all connecting to this first interface. And this interface is usually set to IP mode, access point mode. Then there's a second interface, which is facing the mesh side. It's usually set to ad hoc mode or 802.11s with no forwarding enabled. Those are the 2 modes you can currently select in Gluon. And this interface is used for the communication from node to node and to build up the whole mesh network. So what we did in Gluon now is a few easy steps to increase our available bandwidth. One of them is we increase the originator interval, so the interval that batman-adv uses to build up its topology. So basically, we made batman-adv 5 times slower than the default. And Also, we increased the multicast rate on the ad hoc interface from 1 Mbit per second, which is usually the default, to 12 Mbit per second. So, and as you might already know, that when a vendor writes, this router offers 300 Mbit per second rates, then you usually do not get this, but instead it's more, as a rule of thumb, half of this. So effectively, we might have just 6 Mbit per second now. And one of the good things already is that, at least for Batman 4, that makes the route decisions a little better already, because we do not choose really good routes at a very low rate, but it's a little nicer to have some routes which are a little more, have a little more capacity. So on the IP side, for the left one, we did a somehow similar approach, but not the same, not quite the same. Instead, we have an option in Gluon that you can remove low rates completely. So what many communities are now starting to do is they remove the old 800.2.11 rates from the 1997 standard, or from the 802.11b standard, so that the minimum rate is actually 6 Mbit per second, or the effective rate is 3 Mbit per second. So, okay, so what kind of overhead do we actually have on the multicast layer on top of Batman Advanced? This is a measurement I did a couple of years ago in the Frei von Glübeck community, and we already see that a large portion, for one thing, was for ARP and ICMP version 6. So this is basically related to the addresses we have and address resolution. I think this capture was still before the distributed ARP table was implemented and used. Yeah. And then we also have a few other protocols like SSDP, LLMNR, or MDNS. So a lot of overhead is coming from service discovery protocols as well. And I guess today we even have a much longer list, or would have a much longer list, because there are more and more new protocols coming up which are using fancy multicast things. So how did we tackle this in Gluon? Well, actually, we tackled this the hard way. We just filtered all multicast. Well, but if you do this, you have to be careful. If you really filter all multicast, your network would just break. Because like we've seen before, ARP and DHCP are essential. So those are two exceptions we are making. We are excluding ARP and DHCP because that's what Batman Advanced can handle. And we are also accepting ICMP for version 6 from this. So, but of course, if you're making exceptions, you also have to be prepared to make exceptions for the exceptions. So sometimes we are seeing some strange ICMP version 6 traffic, for instance. Can anybody come up with a very simple packet which you can send onto the link, which every host will answer to? Which broadcast? Yes, broadcast echo, ping of, yeah, ICMP echo, or kind of a ping of death. But in this case, so if a host were sending this out and every other host in the network were responding, then it's not the whole network which is going down, but it's the node where the echo request comes from which is going down. Because it's like an avalanche, all hosts respond, and this one poor node will get all the responses. So echo requests for a broadcast address or multicast addresses in general are also filtered in our case in Gluon. Then a second thing we've observed from time to time are some funny MLD messages, and it happened in some communities. And in a nutshell, we are also having a package now to be able to filter this. But MLD is actually a very interesting ICMP version 6 type to look at, because MLD stands for Multicast Listener Discovery. So what's that, Multicast Listener Discovery? Well, it's a protocol for IP version 6 to enable multicast routing. So instead of just sending a packet from A to B, with multicast you can also send a packet from one host to several hosts. And in the IP world, in the IP version 6 world, it's MLD to do this. And in IP version 6, you might have heard of IGMP, the Internet Group Management Protocol. So how it usually works is that you have a multicast router. This multicast router is asking your network, is there anybody interested in any kind of multicast stream? And then any listener who has some interest in a stream or whatever multicast will respond to the query. And yeah, so the router knows whether it needs to tell the upstream to, can tell the upstream whether it wants to have any multicast or not. So this actually sounds quite interesting because there's also a second use case for MLD. It's not just for multicast routers, but also some enterprise switches are using IGMP and MLD to make their switches smarter. So when you have a switch here in the middle, usually when you send a multicast or a broadcast packet here, it will distribute it to every host attached to the switch. Such smart switches instead will look at the IGMP and MLD messages and will figure out which of these hosts are actually interested in this multicast packet. And instead, the multicast switch can then decide, okay, I don't need to forward the packet to this host or that host. I only need to forward it on this port or on this port. So this kind of sounds like something we want to have in a mesh network as well. We do not want to distribute the multicast packets everywhere, but only to the hosts which are actually interested in this. So do we already have any implementations for something like this? Maybe some code we can look at. Yes, there is. For instance, there is the Linux bridge. The Linux bridge, it's like a software switch. So you can have something like a smart switch in a virtual Linux box. And the cool thing is this Linux bridge already has IGMP, MLD snooping support. And since recently, it also has a multicast to unicast feature, which I might come back later. And right, so it was tricky to get right, the whole multicast snooping with the Linux bridge. Many bugs were fixed in the Linux kernel, but finally we were able to actually get this working. So here is a little graph for the impact the IGMP MLD snooping has on ICMP version 6 traffic. So in this case, I've again taken one of our Fry from Gluon routers, and I've just, I had two routers. One of them had it enabled, one of them had it disabled, and I just had two Wi-Fi clients, and I just emulate or use two USB sticks, two identical ones, and I measured on these two USB sticks how many packets do I get. So initially I was getting about 3,000 packets per minute, so quite a lot. And maybe you did not notice it yet, but here's a second line below here. That's the line I got from the second client. Reduction by 96.7%. And or more on scale, not just for ICMP version 6, but all multicast traffic we have, it was about a reduction by 55.79%. So here's the total multicast traffic, not just ICMP version 6, but also other things on top of Batman Advanced. And this is the new line we get after enabling multicast snooping towards the client device. So what's the green stuff? What is remaining here? It's ARP. So, which is a little weird, and actually a task we want to look at a little more for Batman Advanced at this BattleMesh. Because, well, we have the distributed ARP table, but it somehow does not seem to work 100% in our networks yet, or not anymore with these sizes. So one more task to tackle. However, what about ICMP version 6? Why does it work so well with IP version 6 neighbor discovery compared to, or another question, why aren't we using, or couldn't we use it for things like service discovery as well? Well, neighbor discovery has one very, very nice attribute. It's actually one of the multicast, or I have the feeling it's the right way to do multicast. This one is more using it like broadcast, but this one actually has a very, very nice way of mapping the whole process to specific multicast addresses. And the cool result you get from this is that for one of the things the neighbor discovery needs to do is duplicate address detection. And in this case, in a mesh network, you usually have 0 listeners. So in the common case, you're sending out your multicast package and you see, oh, okay, there's nobody else claiming this address, so great. So actually, we do not have to distribute it into the network at all. Then the second use case for neighbor discovery is address resolution, so the ARP kind of thing as well for IP version 6. And in this case, we usually have just 1 listener. So that's basically the reason why we see such a high, such a nice drop from this high, or this nice 96% reduction, because actually you can just drop many packets with this. So, okay, it works well, but in this case, like I said, I use these sticks here, which are not really doing any meshing. So it's just on this last mile, as you can see here. So the IP interface in the Gluon architecture. So, of course, we want to have the same kind of awareness and reduction of multicast overhead in the whole mesh network. So how can we do this? Well, since the Batman Advanced version from last year, the 2016.3 version, we now have a multicast-aware implementation in Batman Advanced, which is basically just querying the bridge. So the bridge is learning the state regarding multicast listeners for us, and then we just ask the bridge, okay, which host is actually interested in which kind of multicast? So that's been implemented, and the new forwarding routes in Batman Advanced are the following. If there are 0 listeners in the whole mesh network, if none of these 1,500 hosts is interested in this multicast, we can just drop it. And if we notice there's 1 listener, we have a second optimization, which is instead of flooding the network, we're just sending it via unicast to this specific node. And yeah, graphs. Unfortunately, it's already all included in the recent Frei von Gluon master branch. However, there's not been any release yet, so that might be a little graph to show maybe next BattleMesh. But I'm already quite curious and quite optimistic that it should have a similar impact like we saw for the last mile of the mesh network on the AP interface. So, as a summary, so indeed layer 2, it's a very noisy and wild environment by default. And the layer 2 essentials are basically optimized by Batman Advanced, and the layer 2 non-essential stuff, it's just filtered by Gluon with EB tables rules. So, what are the next steps? We, of course, still have to investigate what's going on with ARP, why it's not, how we can get rid of the ARP overhead here too. And the remaining overhead is not anymore so much for the layer 2 specific part, but more the 66 kilobits per second we were seeing in the very first graph regarding the protocol itself. So the next step after these multicast awareness additions would be to look a little closer at the routing protocol itself, and for that there's been already quite some work with a Batman 5 algorithm. And a third point to look at is, of course, it would be nice to further utilize all this multicast awareness we now have, so that we maybe might think of doing things like multicast streaming again. Okay, so this was basically my presentation for now, and if you have any questions, please feel free to ask.
Are there any questions from the audience? I don't see any. Really?
Was it too fast? Shall I repeat some things? Or
is there anything unclear?
So you are part of the Gluon team, right? And in which sizes do you see Batman networks right now? And
Right now, I think the first networks reached 1,000 nodes. Most or a lot of networks are maybe at around 300 to up to 800 nodes maybe. So yeah, that's quite a lot.
I can tell for Chemnitz we have round about 300, between 300 and 400. So, any other questions? We have plenty of time. There's a question for a pause. So, yeah, if there are no further questions, I think you're still available offline. Thanks for your talk.
Thanks.